Welcome to The Explainer. Today, we're diving deep into one of those really fundamental but super tricky challenges in modern software. You know, making copies of data and then, somehow, keeping them all in sync. This whole process is called replication, and trust me, it's happening behind the scenes in pretty much every single app you use.
You know, this quote from the late, great Douglas Adams it perfectly captures the spirit of what we're talking about today. See, with replication, we're trying to build these super robust systems that just don't fail. But the funny thing is, the solutions we come up with, they can create these totally new, bizarre, and, impossible seeming problems. And when things go wrong in this world, they tend to go spectacularly wrong.
All right, so here's our game plan. First, we're going to tackle why we even bother making copies of data in the first place. Then we'll dive into 3 classic strategies for managing them, and I like to think of them as political systems. You've got the dictator, the committee, and, well, total anarchy. After that, we'll look at the strange price you pay for speed, and then we'll wrap it all up with the one single crucial trade-off that every single one of these systems has to make.
Okay, Section 1, the copy conundrum. So first things first, why go through all this trouble? Why keep all these copies of the exact same data? Well, it really boils down to 3 huge wins.
First up, reducing latency. If you can put a copy of your data closer to your users, say someone in Europe gets data from a server in Europe, their experience is just going to feel way faster, way snappier. Second, you get a massive boost in availability. Think about it. If one server with a copy just dies, or maybe it's down for maintenance, no big deal. The whole system just keeps humming along using one of the other copies. And third, you can handle a ton more traffic. We call this read throughput. When you've got thousands, maybe millions of people all trying to read data at the same time, you can just spread those requests out across all your copies. But here's the thing. Making that first copy? That's the easy part. The real challenge, the hard part, is figuring out what happens when that data changes. And that, right there, is where our 3 main architectural patterns come into play.
All right, let's kick things off with the most common, the most straightforward approach out there. Leader-based replication, or as I like to call it, the dictator.
So the idea here is really simple. You pick one of your copies and you anoint it the leader. This leader is now the one and only source of truth. Every single change, every write to the data has to go through the leader first. All the other copies, they're just followers. Their only job is to line up, get the latest changes from the leader, and update their own local copy. It makes for a very orderly, very predictable system.
So here's how a write actually goes down. A user's request to change some data, it gets sent only to the leader. The leader writes that new data down in its own storage, then it turns around and sends that change out to all of its followers. And finally, each follower takes that change and updates its own copy. It's a really clean, simple flow. But it brings up a super important question. Does the leader need to wait for the followers to say, yep, got it, before it tells the user their change was successful?
And that one question, right there, leads us to a massive trade-off. On one side of the coin, you have what's called synchronous replication. The leader waits for at least one follower to confirm it got the new data before saying success to the user. This is way safer, right? You know the data is on at least 2 machines. But what if that follower is slow or it crashes? Well, then your whole system can just grind to a halt. You can't process new writes. On the other side, you've got asynchronous replication. This is super fast. The leader just shouts out the change and moves on. But it's a huge gamble, because if that leader fails a split second after confirming the write, but before any follower got the message, that data is just gone. Poof, it never really existed anywhere else. So you see the constant battle here, performance versus durability? But okay, what happens if the dictator itself fails? Now this is where things get really, really interesting. And pretty dangerous. So when a leader goes down, one of the followers has to step up and be promoted to the new leader. We call this failover. But what if the old leader wasn't actually dead? What if it was just disconnected from the network for a minute? It might wake up and still think it's the leader. And now you have 2 leaders accepting rights. This is an absolute catastrophe known as a split brain scenario. To stop this from happening, systems need something called fencing. And maybe the most vivid term for this is stoneth. It literally stands for shoot the other node in the head. It's a real mechanism to forcibly, and I mean forcibly, make sure the old leader is completely disabled before a new one can take over. It just goes to show you the high stakes involved in making absolutely sure there's only one dictator at a time.
Okay, so the dictator model is simple, but it has that one huge weakness, right? A single point of failure for every single write. So what if we try to fix that? What if we have multiple leaders? And that brings us to our next model, multi-leader replication. I like to call this one the committee.
So in this model, you've got more than one node that can accept writes. This can be awesome for performance, especially if you have, say, a data center in the US and another in Asia. But it creates a huge problem. Just look at this table. What happens when two people try to change the same exact thing at the same time, but on different leaders? So user 1 changes a page title from A to B on the first leader. At the exact same moment, user 2 changes that same title from A to C on the second leader. Now, both of their writes succeed on their local leader, but when those two leaders eventually talk to each other to sync up, which title is correct? Is it B or is it C? The system now has two totally valid but completely contradictory versions of the truth. This is called a write conflict, and it is the absolute central problem of the committee model.
Now, a really common, I'd almost say brutal, way to solve this is a strategy called last write wins. It's dead simple. You just slap a timestamp on every single write, and whichever write has the latest timestamp, well, it wins. The other one, it gets thrown away, silently, gone. So yeah, it forces a decision, but think about the terrifying side effect. A user gets a message saying, yep, your change was saved successfully, only for that change to just vanish into the ether a few seconds later. Without any warning, that's data loss, plain and simple.
Okay, so all this complexity with leaders and committees, it brings us to our final and definitely most radical model. What if we just got rid of leaders completely? Welcome to leaderless replication, or as I like to call it, the anarchy. This is an idea that was really popularized by Amazon's famous internal system Dynamo.
So instead of a dictator calling the shots or a committee trying to agree, we basically have a vote. When a client wants to write or read some data, it doesn't just talk to one server. It sends its request out to several replicas at the same time. And the operation is only considered a success if it gets a minimum number of ayes or acknowledgements back. That minimum number of votes you need, that's what we call a quorum.
And believe it or not, this whole idea is held up by a surprisingly simple formula. W plus R is greater than N. Let me break that down. N is just the total number of replicas you have. W is your write quorum. That's the number of nodes that have to say, I got it, for a write to be successful. And R is your read quorum, the number of nodes you have to hear back from to consider a read successful.
So let's make this real with the example on the slide. Imagine we have 3 total replicas, so N equals 3. We can decide to set our write quorum, W, to 2, and our read quorum, R, also to 2. So does 2 plus 2 equal more than 3? Yep, 4 is greater than 3. The rule holds. And here's the magic trick. As long as that formula is true, you are guaranteed that the set of nodes you read from will overlap with the set of nodes the last write was sent to. There has to be at least one node in common. And what that means is you're guaranteed to read the most up-to-date value, all without having a single leader as a single point of failure.
All right, so we've walked through our 3 models: the dictator, the committee, and anarchy. But pretty much any system that's trying to be fast uses asynchronous replication. And they all share this one common, totally unavoidable problem: replication lag. This little delay creates a state that has a fancy name: eventual consistency. And let me tell you, it comes with a price. So eventual consistency is basically a promise. It says, hey, if everyone just stops making changes for a little while, all the copies of the data will eventually match up. But that keyword, eventually, it's doing a lot of work there. Eventually could be a few milliseconds. It could also be a few minutes. And during that little window of time, different users looking at the same system can see totally different versions of the truth. And this isn't some abstract academic problem. It creates some genuinely bizarre experiences for users.
I'm sure we've all felt this. You post a comment on a website. You hit refresh, and it's gone. You panic. You hit refresh again, and poof, it's back. What in the world is going on? Well, it might not be a bug at all. You could be looking at a direct side effect of replication lag. It's an anomaly with a cool name, a non-monotonic read. So here's what's actually happening under the hood. The first time you refreshed, your web browser's request was sent to a server, a replica, that was totally up to date, so you saw your new comment. Awesome. But when you hit refresh a second later, your request got routed to a different server, and this one was lagging behind. It hadn't gotten the news about your new comment yet. So to you, the user, it looks like time is literally moving backwards. It's like reality is flickering. And there are other weird side effects too, like writing something and then not being able to read it yourself, or the classic example, seeing an answer to a question in a forum before the question itself has appeared.
Okay, so after digging into all these different architectures and their really weird side effects, we finally arrived at the one single fundamental truth of all distributed systems.
And it's this: there is no single best model. There's just no perfect answer. The choice is always a trade-off. You can go with the dictator model. It's simple, it's consistent, but it's got that single point of failure. It's fragile. You could choose the committee. You get high availability for writes, which is great, but now you have to deal with these messy, complicated conflicts that can literally lose people's data. Or you can go with anarchy. It's incredibly fault-tolerant. It can survive almost anything, but you pay for that with weaker consistency guarantees, which leads to that strange, flickering reality we were just talking about.
And that brings us to the final question, the one I want to leave you with. Think about the apps you build, or even just the services you use every single day. What guarantees are they truly giving you? Because the next time you see a piece of data appear and then mysteriously vanish, or an edit that just doesn't seem to stick right away, you'll know. You're probably not looking at a bug. You're likely witnessing a deliberate, fundamental architectural trade-off playing out right in front of you. That little ghost in the machine, it's not a ghost at all. It's just the architect's choice.